Good morning, everyone. Anu was planning to come here, but he couldn't make it. So on behalf of him, I'm reporting the outputs and outcomes of TCCAM that looked at chloride transport in alkali-activated materials. So the 283 CAM TC started off in 2018, and I kind of joined in mid 2019. And then it lasted until 2023 August. So it was it was sort of the normal duration of the TC. But we had roughly 45 members from different parts of the world participating in this work. And the work was essentially divided in kind of two working groups with Anu Castel as the working group leader for looking at performance-based specifications for alkali-activated materials, whereas myself looking at chloride binding capacity of alkali-activated materials, but also looking at synthetic phases that could potentially feed into sort of any modeling work that comes out of this. So the objective of working group 1 was essentially to provide accelerated methods and protocols that could be used for testing concretes made out of alkali-activated materials, and somehow come up with a performance requirement that would allow for its durable performance. So why a performance-based approach for a lot of these materials? They, of course, vary in composition quite significantly. And the number of activators that you potentially use are also varying from going from alkali hydroxide silicates to some near-neutral alkali salts. So this variability poses actually a very big problem if you want to keep testing on or getting consistent, reliable tests to determine how you judge the performance of these materials. And of course, they're very different from normal Portland cement. A lot has been said about that, so I'm not going to dive into too much details on that. So a performance-based approach allows us consistent durability testing. Also is suitable for, must be suitable for exposure conditions that are already in different standards. And also compare this particular performance to a suitable reference concrete, which could be Portland cement or Portland cement-based materials. And it either must perform equivalent to that particular reference material or perform better. And that's how we could judge whether it would be nice to have classifications based on this particular performance method. So this work was essentially looked at in Australia, where Anu is based. So we had a reference concrete of normal Portland cement with two different compressor strength grades, and the targeted service life for these was estimated to be roughly 50 years according to the Australian standard. And these were considered to be the reference concrete. So there was two different test methods that were used in our testing campaign. One was the accelerated rapid chloride permeability test, which is quite a lot used for Portland cement-based materials. But of course, this has a voltage that where you apply 60 volts and see the amount of charge passed. But you also have the long-lasting labor-intensive bulk diffusion test. And So, and somewhat modifications of that with the NT bill 443. The problem with the normal RCPT test when you apply 60 volts to a lot of alkali-activated materials is that these tests fail. The sample gets overheated. The ionic strength of the pore solution does not allow you to accurately kind of measure or measure reliably the charge passed through the sample. So in Australia, with Anu and Noshini, they created a modified version of RCPT, or the ASTMC 1202 method, where instead of using a 60 volt 60 volt potential or potential difference, what they started using was a 10 volt voltage for these particular binders. And this allowed for all the tests to actually be completed, where you have your reference open ordinary Portland cement concretes showing somewhat a lower value compared to these binders over here, which were essentially highly based on alkali-activated fly ashes or metakaolin. So very high volume fractions of these two different materials. But as soon as you kind of increase the amount of slag in your binders, you start seeing this particular, the total charge passed through the system to be very less. And for this particular working group, we'd really like to thank the University of Toulouse, University of New South Wales, Sydney, RMIT, and UTS. We'd like to really thank them for doing some of the work. A lot of different precursors were investigated, so ranging from fly ash, blast furnace slag, calcine clays, ferronickel slags. Just to give you a bit of details as to what kind of mixed designs were used. So in University of New South Wales, we had a lot of fly ash in the binders activated with sodium hydroxide and different grades of sodium hydroxide and sodium silicate. In Toulouse, we had Martin Sir and Gabrielle Sampson helping us with sodium carbonate activated blast furnace slags. Dave Law from RMIT looked at different blends of fly ash and slag. And Anu himself in his lab carried out quite a few tests on different types of slag, fly ashes, calcine clays, also 1 part geopolymers with different activators. So essentially what Anu was, when he was leading this working group, he was trying to he was hoping he gets something like this, where you have the total charge passed versus the apparent diffusion coefficient measured via the ASTM 15 or modified NT build 443. And what they could see is that all of the binders that had significant amount of fly ash or metakaolin basically displayed a very high chloride ion permeability. The reference OPC1 and OPC2 was sort of lying over here between 200 and 600 coulombs, whereas binders that had a very high amount of slag content all displayed very low chloride ion permeability. Now, of course, we don't want to differentiate between different chemistries, but that was just for you to know. Anu and some other colleagues, actually all of them who were part of this experimental campaign, are currently drafting a recommendation where you have a low chloride ion permeability, which essentially is charge past less than or equal to 200 coulombs, and then the medium and the high chloride ion permeability. Essentially what this says is anything with less than 200 chloride ion coulombs pass. These concretes are suitable for being used in chloride environments, including even very severe conditions such as tidal zones. The stuff which has a high chloride ion permeability, of course, not suitable for chloride environments, and where we have a medium chloride ion permeability, it may be possible to use them for moderately severe chloride exposures. These are possibly located in coastal areas without any direct contact with seawater. But what our colleagues are basically proposing is that the ASTM C1556 bulk diffusion test should be carried out to confirm their suitability for more severe environments. So now we move on to working group 2 and its objectives. In working group 2, we were looking at how chloride binds in alkali-activated materials and also synthetic phases that generally form as hydrate products or reaction products in alkali-activated materials. Now, we, of course, restricted ourselves to alkali-activated slags because it's very well known that alkali-activated fly ashes and other clay-based alkali-activated materials have a very high chloride ion permeability. So the likelihood of investigating chloride binding in those or the likelihood of them being used for any severe environment would be quite less. So we know the major hydrate phases all in alkali-activated slags as well as in blended cements. We've got the cache phase, we've got AFM phases, possibly stratlingite, and in Portland cement-based systems, a bit of Portlandite. We also know that Portlandite and ettringite do not contribute to chloride binding. At least that's what the literature data says. And the chloride binding in these particular materials is dominated by the cache and the AFM phases. So we looked at some of the literature work that was done in these regards. There are, of course, quite a few studies, but we've just cited some of these two particular papers or works by our colleagues Shinwan K and Hirao. And they looked at chloride binding in cache as well as in CSH. And what you can see is a typical isotherm that you would expect for the CSH phase. You can argue whether it's Freundlich or Langmuir. But for the cache phase, you actually don't see anything or any isotherm that could be reproduced. But you can see the discrepancy in the amount of chloride that can bind within these two particular studies. The other thing is when you move towards synthetic phases, where you've got meixnerite, which is the MgAlOH LDH, or where you've got monosulfate or stratlingite, and all of these, in some of the cases, they actually have reported chloride binding to be in excess of what's theoretically possible. And this depends on maybe possibly some of the experimental parameters they use. So we essentially went from there on, and we wanted to look at all these synthetic phases, produce them in the labs, and additionally also look at alkali-activated slag samples with different activators. So we kind of produced monosulfide, stratlingite, hydrotalcite, and meixnerite. And we were fairly successful in producing most of these synthetic phases. There's a lot of work that was done prior to us on how to synthesize these. So we kind of happily followed their protocol. Of course, there are some impurities. For example, in the monosulfate, you see some ettringite also forming. And from there, we kind of looked at, then we looked at how these alkali-activated slags with different activators cured. And what we could see was there was some amount of carbonation for all of these particular different activators. But what, as one would expect, there are different hydrate phases formed in all of them. For our chloride sorption studies, we looked at a very simple setup. We had some already existing data from Xin1K, looking at chloride concentrations up to, or free chloride concentrations going up to 0.6 or 0.7 mole per liter. So we also took the opportunity to extend that data set. And then we dispersed all these solid powders, actually fairly fine, in chloride ranging from 0.1 to 1.4 molar. But what we ensured was that the ionic strength of these particular solutions was constant. And then we looked at various liquid-solid ratios that are used for studying chloride binding. And then we went from a really low value of 13, going all the way up to 108. And for the alkali-activated slags, we kind of restricted ourselves to one particular liquid-solid ratio. Then, the normal procedure for analyzing aliquots, trying to equilibrate it for 21 days, and then shaking it or swapping it after 3 days a week. And then withdrawal of this particular aliquot, analyzing the amount of chloride in the supernatant solution. So let's see what we got for monosulfide. So chloride binding in the monosulfide phase almost approaches its theoretical chloride binding capacity, which essentially means that 1 chloride per interlayer site is replaced. But this changes as a function of the liquid-solid ratio that you use. So if you're using a liquid-solid ratio of 53, at least that's what we used, and if you keep on reducing that particular liquid-solid ratio, you never kind of reach the theoretical chloride binding capacity. The same goes for stratlingite. Stratlingite also can bind chloride, and at higher liquid-solid ratio, you again see almost theoretical chloride binding happening. Kind of increases from 0 to 0.75 free chloride, and then sort of flattens out with an error bar. But when you reduce the liquid-solid ratio, the amount of chloride bound is far less than the theoretical one that's expected. And in the case of meixnerite and hydrotalcites, chloride binding far exceeded its theoretical binding capacity when we look at meixnerite with 108 liquid to solid ratio. Of course, we had troubles making some of these synthetic phases or the amounts we could make. So we were restricted by the number of experiments we could do there. And, but when we look at liquid solid ratios of 26, these particular chloride binding capacities are way, way below the theoretical chloride binding capacity. And this was essentially confirmed by our X-ray diffraction results on the monosulfate and stratlingite. We looked at selected samples. So from if you look at the monosulfate, we go from starting forming Kusel salt, and this at roughly 1 to 1.4 and 1 mole per liter of free chloride. And this essentially says that it's not completely gone into Friedel salt. And for stratlingite as well, what we can see is quite a lot of peaks of Friedel salt, but some of the stratlingite essentially remains there, which essentially tells us that it's partial chloride binding rather than complete chloride binding. Now we tried to compare this with what one would achieve with thermodynamic modeling, looking at the theoretical binding capacity. So in the case of monosulfate, what we found was that the chloride binding, complete conversion of, or complete formation, or the entirety of chloride is bound in the form of Friedel salt at roughly 1 mole per liter of free chloride concentration. And the same, but when you look at a higher liquid-solid ratio, you start forming Friedel salt at roughly 0.75 mole per liter free chloride. This is far lower or a lower value compared to what we could kind of see, particularly with the low liquid-solid ratio. Now, if you look at stratlingite, again, we see that the complete conversion of stratlingite to Friedel salt happened at much lower values when we look at the theoretical chloride binding capacity for free chloride. And this kind of pinpoints that chloride binding isotherms of LDH AFM phases cannot be sort of predicted at the moment properly with only thermodynamic modeling or just looking at the theoretical chloride binding capacity. They also depend strongly on the liquid-solid ratio that you employ in your experiment. And this possibly might be the reason why we have significant deviation in the available data in the literature. We could not possibly answer why there is a discrepancy. Why would the chloride binding capacity increase when you increase the liquid-solid ratio? And this remains an open question, and we are looking forward to solve it with other colleagues. But another interesting question is how to implement these results in chloride binding models. Because the liquid-solid ratio that one might apply in mortars or concretes might be very different to what might be actually much lower. So you might not really capture the correct value of or the correct isotherm. So moving on to chloride binding and alkali-activated slag paste, what we saw was that for all of the activators, they fairly showed similar chloride binding as a function of the isotherm, as a function of the free chloride content in the solution. And these were tested in 2 different laboratories. So there was, we could discard the possibility of an error. But with the shape of these chloride binding isotherms in alkali-activated slag paste resemble those fairly nicely of the individual layered double hydroxide or AFM phases, at least at high free liquid-solid ratios, and yeah, up to a free chloride concentration of 0.9 to 1.1 molar. The chloride binding capacities of these by the AAS paste was somewhat higher than what was reported for most conventional pastes in sodium chloride solutions, well, almost twice. And yeah, the moderate differences between different alkali-activated slag pastes with different activators can be explained quite with a reasonable amount of confidence that different hydration products cause different amounts of chloride binding. And we can see that. And the last point I wanted to sort of bring up was that the steep increase of the chloride binding in the alkali-activated slag paste, when you are at a very high concentration of chloride, free chloride, is somewhat differs from normal conventional cement paste. But of course, the number of experiments that we have are very limited. And we don't know why that kind of happens, but we think that it might be related to the C-Nash phase that we form. So just to rephrase this, you don't see the Freundlich or the Langmuir isotherm, so where the bound chloride starts becoming constant as you keep on increasing the chloride concentration. So just to wrap up, there are two outputs expected from this particular TC. The first working group is currently working on a performance-based approach RILEM TC recommendation, whereas the second working group, we published a paper recently in Materials and Structures on chloride binding in layered double hydroxides and alkali-activated slag base. And on behalf of Anu and me, we'd love to thank all the RILEM members that were part of this TC who contributed in any particular form. It was a bit sad we couldn't meet a lot of times, but it was nice to see all the faces online. And thank you so much for your attention.